All right, so we're going to approach this as kind of a rapid review of the trigonometry course. Some of you are, I know, are going to pre-cal, first semester and second semester calculus, so it might be a review for some of you, but at least it'll strengthen your understanding of where trig came from and what is the relationships in terms of side lengths of this little diagram here of the trig functions, the 6 main trig functions. What are the 6 main trig functions? Do you know any of the trig functions?
Cosine, secant, tangent, cosine.
Yeah, you said cosine, secant, and then cotangent, tangent, and then sine and what's the missing one? Cosecant, yes. You're here again?
I don't know the topic.
You don't know the what?
I don't know the topic, that's why.
Oh, this is trigonometry. I thought you sat through this one, but okay. Anyway, okay, let's get started here. First of all, let's talk about trig. Trig review. First of all, where did trig come from, and who invented trig? Newton, yeah, it was Newton. Yeah, it was Newton. It wasn't Archimedes, it was Newton. And so what he did was he looked at a unit circle. Now let's start with that. Okay, if we call this the unit circle, let's talk about why is it called the unit circle? Let's move it off here. Why is the unit circle called the unit circle? Can anybody tell me that?
Radius is unit of 1.
Yeah, because the radius is 1 unit. Very good. Now, what's the standard form for the equation of a circle in general? That's centered at the origin. It should be x minus h what? Squared plus y minus k squared equals what? No. R squared. That was the standard form, right? Now, for the unit circle, where is the unit circle centered? The unit circle is centered at the what? Origin. You have to remember, when we talk about the unit circle, specifically for this review, we're talking about a circle that's centered at the origin whose radius is 1 unit. Okay. And the equation for the unit circle, some of you already said it, it's what? X squared plus y squared equals what? 1. What's the coordinates right here? What's that ordered pair? 1, 0, right? That makes sense? Yeah, graphing. What's this coordinate right up here? 0, 1. And this coordinate here, -1, 0. And this coordinate down here is 0, -1. Okay, they're right there. So one of the things I want to convey to you is when you're asked to evaluate trig values, like what's the cosine of 45? What's the sine of 30 degrees? You here for the trig review? Trig review?
Yes.
Okay, yeah, pass one of these back to him. Okay. Just to prep you for this review here, I want you to understand that when you're asked to find, say, the cosine of 30 degrees, all you're really being asked to is to give the x coordinate of a location on the unit circle that's dependent on that angle 30 degrees. And this is what Newton was looking at. Now, back then, they were in geometry, they were talking about, angles and rays. And so Newton looked at where a ray originated from the origin and where it intersected the unit circle. So this is your ray. This is defined to be the angle theta. And to start off, we're going to say r theta is always measured from the positive x-axis. And when you see, as theta changes, the ordered pair that the ray intersects the unit circle is going to change, correct? Right? When the ray is up here, if you had an angle up here, if your ray was this way, this theta would be even larger, right? Obviously, that would be a different theta, and that would be that ordered pair there, right? Now, which of the two ordered pairs has the larger x value? The first one, right? Correct? Because this x value is where? Right here, right? That would be if I dropped a perpendicular down to here, this would be its x value. And if I dropped a perpendicular down here, its x value would be where? Right there, correct? So which has a larger x value? That one, right? And which one has a larger y value? Obviously, this one, right? And so you're going to find when doing trig and trying to evaluate trig functions, specifically sine and cosine, you're really just asked to find the x and y coordinates, okay? So in alphabetical order, cosine theta, sine theta, right? C comes before S, correct? And in alphabetical order, x comes before what? Y. So to remember, when you're looking at a cosine, you're looking at an x coordinate, right? And when you're looking at a sine, you're looking at a y coordinate. So on this picture here, you see, this is the unit circle with all the ordered pairs filled out. And so if I were to ask you, watch, we're going to do some trig. You haven't had the trig class, right? You have had the trig class, okay. Well, you have a little bit. Okay. So if you go to the unit circle here and say, let's go to the ordered pair at 30 degrees. Now, how much is 30 degrees? Where is it on the unit circle? Which quadrant is that in?
First quadrant.
Yeah, the quadrants go what? 1, 2, 3, 4. So 30 degrees. Go to 30 degrees on the unit circle. What ordered pair is at 30 degrees?
Root 3 over 2
And 1/2. Do you see it? Do you know where 30 degrees is?
Yeah, it would be
Where's-
in 30 degrees, wouldn't it be in?
Okay, we always start from the what? Positive x-axis. 30 degrees would be the first one. This would be 30 degrees.
Okay, so it'd be quadrant 1.
Quadrant 1, and what's the ordered pair there?
The ordered pair would be square root of 3 over 2.
Two.
And then it would be, for the y, it would be 1 over 2.
1 over 2, right? So the x-coordinate is root 3 over 2. The y-coordinate is 1/2. So when you're asked to evaluate the cosine of 30 degrees, you're really being asked to give the x-coordinate. What's the x-coordinate at 30 degrees?
So the x-coordinate would be the square root of 3 over 2.
That's it. That is the cosine of what? 30 degrees, right? What's the y-coordinate at 30 degrees?
1/2.
1/2. That's the sine of 30 degrees, right? Now, what class are you going into?
I already took trig.
Okay.
I'm
Just reviewing. Okay, good. So we're just going through the basics here. Okay, so it makes sense. The equation of the unit circle is x squared plus y squared equals 1. And I was just kind of preparing you by saying x is represented by which trig function? Cosine of theta, right? And y is represented by the sine. So by this identity here, we can say, hey, cosine squared plus what? Sine squared equals 1. That's one of the identities we know, right? Where does it all come from? Well, it's coming from this. A little bit more. There's a little bit more here, okay? And that's what we're going to look at. We're now going to focus on the first quadrant, okay? So Newton realized, hey, all these x, y coordinates change as theta gets larger and larger and larger, right? When theta moves this way, right, where the rays intersect the unit circle, they each have different ordered pairs, right? We said this one has a larger x value than what? That one. This one has a smaller y value than that ordered pair, right? Okay, so let's focus on the first quadrant. Okay, so that's what we're going to do here. And this diagram is in the lower right-hand corner of that handout I gave you. Okay, it's coming like this, comes out to here, something like this. There we go. Okay. Now let's draw the ray originating from the origin. Okay. Let's say the ray is going like this. I'll draw it in red. Here's my ray. It goes out, 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 out. Like that. What's going on? Now we're going to focus first on the point where the ray intersects the unit circle. We can define this ordered pair as some arbitrary x, y value, where this is the x-axis and this is the y-axis. And again, what's this x value right here? What x value is this one right here?
1.
That's 1 because this is the graph of the what? Unit circle. Okay, and what's this y value right here? 1. Right? Okay. And theta will be measured from the positive x-axis. Right there. Okay. Now, let me ask you something. When theta gets smaller, which value is decreasing, the x or the y? When theta gets smaller, closer to 0? Y is getting smaller, right? When theta gets smaller and smaller, y is going to get smaller. Where is the y represented on this ordered pair? It's this line right here. This length represents the which value? The y value, right? And since I dropped a perpendicular down here, this is a right angle. This length right here is the what? Is the x value, right? When you come straight down? And what's the length of the hypotenuse of this right triangle? It's so easy, it's confusing. It's 1. Why is it 1? Yeah, because it's the radius of the unit circle, correct? So this is 1. That makes perfect sense because by the Pythagorean theorem, how do you relate x, y, and 1? X squared plus y squared equals 1. That makes perfect sense because that's the equation of the what? Of the circle. Now what's important here is that we have a right triangle here. And I'm going to draw it separately over here. Okay. Here's my right triangle. Remember the hypotenuse was equal to 1. This leg of the right triangle is the y coordinate, y value, and this leg is the x coordinate, right? We know that. Okay, but Newton said, okay, yes, I understand that these x and y values are going to change as theta changes, and that's where he assigned these x and y variables names. And what class are you going into?
3B.
Are you going to 3B? Yeah. So as I mentioned earlier, Newton decided to call x which trig function? Cosine of theta. And the y he called what? Sine theta. So when you look at this x value can be represented by the cosine of theta. And this y value is the what? Sine of theta. So in terms of this right triangle here, instead of calling this x, I can call it which trig function? Cosine theta. And what about this y value? Sine of theta. So that's really that right triangle there. So let me ask you this. And this is important for knowing your graphs. When we say knowing, we're saying not memorizing, understanding your graphs. Because if you understand how these x and y values change as theta changes, then you know how cosine and sine change, and therefore you know how the graphs will go. Because I asked this earlier. When theta gets smaller, closer to 0, which trig function is getting smaller? Can you see sine is getting smaller, getting closer to what? 0, right? And what's the sine of 0 then? Sine of 0 will be 0. What about the cosine of 0? What's the x value when theta gets to 0? Yeah, because you're going to be right here. That's the x coordinate. That's the what? Y coordinate when your ray is right here, right? At an angle of 0. All right. Now, some of you have had calculus already, right? And so you understand the concept of tangent lines. Okay, those of you who have calculus, how do you describe a tangent line?
The line. A line that only touches the curve once.
Yeah, it only touches the curve once, right? But in a specific way. When we say, just a quick little note here, I'm going to put it real small right here. If you have a curve like this, okay, we're not saying, and you look at a point here, there's many ways to draw lines that intersect the curve only once. I could draw it like this, like this, like this, and so on, right? But a tangent line specifically intersects it at one point, and it looks something like this. Okay, and this would be a line that's tangent to this curve, okay? I need to kind of mention this so that we have an understanding of possibly why Newton called this the tangent function and the cotangent function. Because Newton realized, hey, okay, as theta changes, these lengths are going to change, x and y. But then Newton looked at, oh, what about a line that's tangent to the circle? A vertical line tangent to the circle like this. How does that line intersect the ray? Well, if I think of it right here, here's my tangent line from the positive x-axis up to the ray. Okay, right there. Let's go right here. All right. And notice here, we have a slightly bigger circle than the first, correct? This one's bigger.
Triangle.
I'm sorry, triangle, thank you. Bigger triangle, right? Now let me draw that triangle separately over here. It's green, right? I'm going to draw it right here. Okay. My eraser. Let's draw it. That's good. And we'll draw it about right here. And about right here. Okay, there it is right there. Okay, where is theta? Theta was right here. Theta is also right here. And these are both right triangles. And because this is 90, this is theta, that's 90 minus theta, that's 90 minus theta, we can classify these. Oh, I have another one. That's good. We can classify these triangles as being similar. All right, so now, this length here is coming off the vertical tangent line, right? And we notice as theta changes, as theta gets smaller and smaller and smaller, this length is also going to get what? Smaller, right? Correct? And because you can think of it as tangent to the unit circle vertically, Newton gave this length a name. Which trig function do you think he called it? Since it's coming from a tangent line.
Cotangent?
Or the tangent. He actually called it the tangent. This is tangent of theta. Okay? Now let's think of a line that along the ray that connects from the origin to the tangent. Okay? We know this is tangent. What about this length here? Okay? That one we have to think about. He gave that one a name. What about the bottom one here? What's the length of the base of this particular triangle? Now, cosine only runs up to here. What comes all the way across? It's 1, correct? Isn't it 1 for the base of this triangle? You see it? It's 1. Okay? Now, if you go back to geometry, if we take 2 points on a ray and we define a line on those 2 points, that's called a secant line. So what do you think he called the length that runs from the origin up to where it connects the tangent? He called that the what? Secant of theta. And so we have secant of theta here.
And that goes back to the Pythagorean identity, right?
Yes, so that's again, if we apply the Pythagorean identity to this triangle, what identity do we get? 1 plus tangent squared equals secant squared. Okay? So let's write that out here. Over here, we're going to say we know from here cosine squared theta plus sine squared theta equals 1, right? That's from that one. What identity do we get for this one? 1 plus what? Tangent squared theta equals what? Secant squared theta. Okay? That should make perfect sense. It's just the Pythagorean identity. That's why they're called the Pythagorean identities. Okay, now, important thing. We said, hey, these two triangles are similar. And we know from geometry, or back, actually, you started this back in beginning algebra. Did you take beginning algebra here? No? Okay. Back in high school, whenever you had algebra, there was a thing that talked about similar triangles. And that rule said the ratio of corresponding sides of similar triangles must be equal. Okay? And so look at it right here. We can say, oh, wait a minute. Look from here. Sine over cosine. From there, we see, hey, sine theta over cosine theta. Sine theta over cosine has to equal what? Tangent over what? over 1. The reciprocal identity. This is where this comes from, right? You might remember sine over cosine equals what? Tangent. This is why it's there. Now, what about 1 over cosine? 1 over cosine of theta. By similar triangles, what does 1 over cosine equal? Secant theta over 1. So the point is, see, everything is coming from this little picture here. And if you understand how where everything's at, then all these identities make sense. And then you can easily derive them, so you don't have to sit there and try to memorize all this, especially when you're taking calculus. You don't have time you got to memorize other things, right? Let alone worry about trig. And if you're going into trig, right, if you have a little background of it, it might be able to make it a little bit more sensible. Okay, we've got one more triangle to deal with, because we do not see what we call the co-functions here, right? Do you know the names of those co-functions? We're missing the what? Cosecant and the cotangent, right? They're right? Cosecant, cotangent. All right. So I had talked about the vertical tangent line. Well, what about the horizontal tangent line and where that intersects the ray? That would be on the what? Up here off the what? Up the top, up here. And now this diagram is going to be right over here. And there's where it intersects the ray, correct? Now this right here is a right angle, right? And that's at the top. And if this is theta right here, and this is very important here, people get confused on this. We have the x-axis right here, correct? Right here. And then we have this tangent line horizontal up here. What can you tell me about these two lines? They're parallel, right? And if you remember from like beginning algebra, when you have two parallel lines and a line intersecting, what can you tell me about this angle and this angle here? They're equal, right? Those are the alternate interior angles, right? So therefore, if this is theta here, what must this angle be? That also is theta. And then we have the right triangle here, right? Okay, so this vertical tangent line, we're defining that as tangent. From the horizontal tangent line, what do you think Newton called that length? Cotangent, right? Makes sense. That's the cotangent of theta. All right? What's this length from here to here? It's so easy, it's confusing. That's 1, correct? All right. Now, what about the length from the origin to where this cotangent intersects the ray? Okay? He couldn't call it the what? Couldn't call it secant because he already assigned it. So what do you think you call it? Cosecant, the co-function, right? So you can see the cosecant function connects all the way to the cotangent. All right? And so now we have this right triangle. But what we want to do to make it a little bit clear on the similar triangles, we want to orient everything the same way. So I don't want this triangle drawn this way. I want to flip it over this way. So let's see if we can do it. That's the biggest of the 3 triangles, right? Here was our first triangle. Here was our second triangle. And here was the third triangle. So we're going to flop it over like this. And that's our biggest one. We're going to go like this, and like this. Okay, right triangle. Now, what's the hypotenuse of that triangle? What length is that? Which trig function is the hypotenuse of that triangle? That's it goes all the way here, right? That is the cosecant of theta. You see it?
Yeah. I just never knew how it all fit. Like, I know that it was like this whole circle thing.
Yeah.
Like,
But now you're seeing how things fit together?
yeah.
Okay.
I don't remember this at all.
You don't remember this at all?
No, I'm just kind of glad to hear.
Well, a lot of times we take a trig class. I mean, that trig, especially here or wherever else you take it, it's a 3-unit class, and it goes so quickly, right?
Yeah.
This stuff is in the book, but it's not very explicit, right? It's kind of given to you implicitly. Saying that it's like, oh, they assume that you know this stuff, right? But that's why you're here. We're kind of going deeper in this so that when this comes up to you, you say, oh, wait a minute, now I see, right? I have the model in my head to see what they're trying to explain to you, okay? So if this is the cosecant, now what's this length here? This is the shorter length. That's the what? Is that the 1? That's the 1. Right there. Now, what's that bottom length? That's this length, that's that leg up there, right? That's the longer leg. The shorter leg was 1, the longer leg is now what? Cotangent of theta. All right. Now we're going to apply the Pythagorean identity. So if we apply the Pythagorean identity, oh, don't forget theta was right here. If we apply the Pythagorean identity to that triangle, what do we get?
Cotangent squared plus 1 equals cosecant squared.
Cotangent squared theta plus 1 equals cosecant squared theta. There's your third Pythagorean identity, right? You guys have seen those at some point, right? You just don't know where they came from. What'd you do, memorize it all?
Yeah.
I don't know how you can memorize, that's impossible.
Well, anyway.
You were told to do that, right? Okay.
Don't understand it.
Yeah, that's what. I always tell kids, yeah, hey, can you tell me the cosine of 45? What do? They get their calculator. Oh, I know the cosine of 45. Over 2 over 2. No, that doesn't work that way, right? Okay, now that we have our 3 Pythagorean identities, we're going to analyze the relationships of the similar triangles, right? The corresponding sides. We know sine over cosine is tangent. 1 over cosine is secant. Now it opens up a whole new world because we can see, what can we say about cosine theta over sine theta? Cosine theta over sine theta has to equal what from this triangle? Cosine over sine has to equal what? 1 over what?
Tangent.
1 over tangent. And looking at our third triangle, cosine over sine is 1 over tangent, which is what? Cotangent over 1. Can you see it? Did you memorize all those too? Of course, Led Zeppelin. Who's the singer for Led Zeppelin, by the way?
What is it? Oh, throw me on the spot.
I'm just curious.
Is it? No, there's nothing. Jimmy Page is the guitar.
Oh, at least he got that right. Okay,
Yeah.
I'm just making sure. We're going to wear the shirt. It's Robert Plant.
Right, yeah, that's it.
That's my generation. Anyway, okay. What else can we look at? Okay, so we did, how about 1 over sine now? 1 over sine theta. Okay, if we look at the green triangle, 1 over sine has to equal what? Secant over what? Oops. Secant theta over tangent theta, right? Okay. Now we look at the third triangle. What identity do we get? What is it?
Why is that 1 over sine?
Okay, 1 over sine is, okay, we look at it this way. 1 over sine is secant over what? Tangent, which is also cosecant over 1. So that's basically cosecant, right? Cosecant over 1. So this is your reciprocal identity. Hey, 1 over sine is the what?
This is how
It's the
that's
cosine.
how he related all them.
No, he just took geometry and said, oh, I know about similar triangles. But he just looked at this, he just looked at the unit circle and said, oh, here's a ray. Let's look at how all these things change. And there you go, that's trig. This is the whole course right now. Okay, but see, it's all based on what? Similar triangles, correct? See, now, the tricky part now is understanding how all these lengths change when theta changes. Because once you understand that, those graphs that you're doing, like a sine curve, is plotting which coordinate? It's plotting the y coordinate as the theta moves around the what? unit circle. And obviously, once you go one time around, right? One time around, it's going to start what? Repeating. That's why you get periodic functions, right? Okay. Well, we got a couple more to do. What do we have here? We have, okay, sine over cosine is tangent, 1 over cosine is secant, 1 over sine is cosecant. Are we missing anything? What about cosine over sine? We got that. That's cotangent, right? So there's some other things we can say. What makes sense then that 1 over the cosecant is sine over 1, right? That's what we use all the time. 1 over tangent is the cotangent, right? What's cotangent over cosecant? Cotangent over cosecant, which is cosine, right? Cosine over 1. It's all there, right? So a lot of times if you're taking like calculus, if you just draw these triangles here, then a lot of things start coming, right? Because a lot of times I know, like if you've dealt with trig already or in the past, when you're trying to simplify cosecant over cotangent, a lot of people tend to change things to sines and cosines, right? That's what you normally did. Change all the sines and cosines, and then you simplify and you end up with cosine. Like, oh, of course it did that, because the relationships are there, right? They're not all that easy. But anyway. Okay, any questions on this so far? Yes?
I'm just a little bit jumping ahead. But,
Okay.
You know when you have the sine curve?
Yes.
How the tangent one would look would, like, how does that rotate on the circle there?
Okay, we're going to get to that. He's saying, that's a good question here. Let's just talk about that. The tangent curve, okay? Now, the tangent length is right here, correct? Yeah. Now, what's going to happen when the ray the ray was right here. If your ray was drawn, say, right here, the tangent length would be just that big, right? And as theta gets here, tangent length gets that. What about if theta was right here? If your ray went up here, where would the tangent intersect? It would be way up there, right?
Yeah.
But what happens when you're at 90 degrees and the ray is going straight up? What would you say about this vertical tangent line? If the ray is straight up and this tangent line is vertical, will they ever intersect? No, because they're parallel lines, right? That's why the tangent is what? Is undefined at what angle? 90 degrees. That's why it does that. Now, I know a lot of you students were memorizing all students take calculus, right? You ever heard of all students take calculus? Good. Have you heard of please excuse my dear Aunt Sally? That's even worse. Okay. Those are just memorization techniques, right? But let's talk about the unit circle itself, drawn on the Cartesian coordinate system, and let's talk about the 4 quadrants and think about these relationships. In the first quadrant, both the x and y coordinate are what? Positive. So if you look at your little table here, notice in quadrant 1, all those coordinates have what? Positive x and y values, right? That means in terms of the graphs, hey, x represents which function? Cosine. Y represents the sine function. So whenever the x coordinate is positive, the graph of the cosine must be what? Positive, right? Whenever the y coordinate is positive, the graph of the sine thing, right, has to be positive. And now that takes us back to here, and this is how you understand your graphs. See, if both sine and cosine are positive, that means the tangent has to be what? Positive, right? If one of these is negative, the tangent will be what? Negative. If they're both negative, tangent's positive. When is a tangent undefined? When is a fraction undefined? When zero's in the what? So you're thinking, oh, that's a cosine function, right? Then you go back to the unit circle. Oh, cosine is which coordinate? X or y? Alphabetical order, remember? It's the x. So when is the x coordinate 0 on the unit circle? At what angles? At 90, 270, and you can go backwards, right? We'll get to that. So those are the locations of the what? Vertical asymptotes. We'll graph those, and it's all going to tie together, right? Okay, let's look at this reciprocal identity. 1 over cosine equals secant. It makes perfect sense. If 1 over cosine is the secant, whenever cosine is positive, the secant must be what? Positive, right? In which quadrants of the unit circle is cosine positive? Remember, which coordinate are we thinking? X X. That's first and what? First and fourth. Whenever cosine's positive, secant is positive. Whenever cosine is negative, secant is negative, right? Whenever cosine is 0, secant is undefined. So how do you find the locations of the vertical asymptotes of the secant? You look at the cosine, right? You look for the cosine to be 0. Cosine is represented by the x-coordinate. When are the x-coordinate 0? 90 and 2. That's the same as which graph? We just did it. That's the tangent, right? That was the tangent, right? Because look at tangent and secant both have what in the denominator? Cosine. So whenever the cosine is 0, these functions are undefined. That's why the graphs are like. That's why how you find the location of vertical asymptotes, right? And if you think about it in terms of lengths, well, where is the secant curve at? The secant length. It's right here. The secant connects to which one? The tangent, right? So this should make perfect sense. At 90 degrees, the ray is straight up. And the tangent is also straight up. Those two lines are what? Parallel. Therefore, they never intersect, correct? Therefore, since the secant is trying to connect the origin to the tangent, if they're parallel, is the secant going to be there? No, it's undefined also. Okay? Now, let's look at cotangent from our similar triangles. Cotangent is 1 over the what? Or cosine over sine, right? So once again, if cosine and sine are both positive, cotangent is positive, right? If they're both negative, also positive, right? If one's positive, one's negative, then this has to be what? Negative, right? Same with the tangent, correct? So think about the unit circle. In the unit circle, in which quadrants are both x and y, when do they have opposite signs? In which quadrants? In the second and fourth, right? Because in the second quadrant, x is negative, y is what? Positive. In terms of trig, cosine's negative, sine is positive, right? In quadrant 4, x is positive, y is negative, which means cosine's positive, sine is what? Negative. So in quadrants 2 and 4, tangent and cotangent must be what? Negative, right? Those graphs have to be drawn below the x-axis, right? When are these tangents and cotangents positive? In which quadrants? First and third, right? Okay. They're all there. Now, very similar with the secant and cosecant, that relationship, we can see that 1 over sine is cosecant over 1. So, whenever sine is equal to 0, the cosecant will be what? Undefined. When is the sine equal to 0? At what angles? 0 and 180. That's 0 and 180, because remember, the sine represents the y-coordinate. At 0 degrees, your y-coordinate is 0. Also at 180, your y-coordinate is 0, right? So at 0 and 180, that will be the locations of the vertical asymptotes of the what? Cosecant whenever the sine is 0, okay? We'll be doing some graphs, so this will all come together here, okay? All right, so that kind of answers your question more than once. Okay, but that's good. We want to kind of get it. Now, any other questions on this? Now, are we going in the right direction here?
Does the secant and cosecant change in polarity depending on the quadrant?
Yes, but the secant is dependent. We always usually refer to sines and cosines.
Secant, it's the same as cosine. So,
Secant is related to cosine.
Secant would be positive in 1 and 4. Right?
Yeah, because when's cosine positive? In
1 and 4.
1 and 4. Therefore, secant's positive in 1 and 4, right?
Okay, so
So if you, I'm going to do the graph really quickly here. When you graph a cosine, if we draw this part of the cosine, do you remember how the trick to doing the secant? You draw the secant what, like this, right? Remember that? And we taught that.
yeah.
That's why, because if this is positive, right? If the cosine is equal to 1, the secant has to be what? 1. Because what's 1 divided by 1? Take out your calculator. 1, right? But if cosine is 1, secant is 1. That's why it connects to that point right there. If cosine's positive, the secant must be positive. That's why that little trick worked, right? Whenever the cosine was 0, that's when you drew the what? Right? That was that trick. Then you erase that, and then you have the graph of the. Okay. It's right there. Yeah. You ever seen that?
Yes.
Okay. Good.
So, if I grasp the knowledge that you're trying to like pretty much state right now, it's just the fact that it changes from positive to negative, positive to positive type of thing.
Yeah, we're
You're
trying.
placing it like on the unit circle, like in different ways.
Yeah, we're just referencing the x and y coordinates. Because remember, everything is tied to these x and y coordinates, right? But think of it. X and y mean what?
Sine and cosine, right? Or cosine and sine.
And we're saying, since tangent equals sine over cosine, correct? We know that if both sine and cosine are positive, the tangent must be what? Positive. Now, if we think back into the unit circle, the sine actually represents the y coordinate, and the cosine represents the x coordinate. And we know in quadrant 1, both x and y are positive, right? So if both x and y are positive in quadrant 1, that means sine and cosine are both positive, which means tangent has to be what? Positive. So does the what? Cotangent in quadrant 1, correct? So does the what? Secant, because that's 1 over cosine, right? And so does the cosecant, because that's 1 over sine. That's that all students take calculus. Now, some of you have not heard of it. Who's heard of that? All students take calculus. You have? Okay, you have. So what were they saying?
The quadrant 1 is all positive.
Okay, let's stop right there. You're saying in quadrant 1, they're all positive. Yes, because in quadrant 1, everything's positive because both x and y are what?
Positive.
Which means cosines and sines, everything's positive. And so that's what the A was for. And then you came over here to quadrant 2 and said S. What did S represent? That was a sine. Sine is that makes sense because in quadrant 2, which coordinate is positive, the x or y coordinate? In quadrant 2, it's the y coordinate, right? And the y coordinate represents which trig function? Sine of theta. So that's what they were saying there, right? If sine is positive, the cosecant must be positive, right? Okay. Sine is positive, cosine's negative, cotangent will be what? Negative, right? Same with a tangent. If sine is positive, cosine's negative, tangent's negative, right? Cosine's negative, secant's negative. So they said all students, sine is positive, yeah, that gives you all that other stuff. What about in quadrant 3? Okay, it went all students take. What did the T stand for? Tangent. So they were saying tangent's positive. Of course tangent's positive in quadrant 3, but why? Yeah, basically it. Because in quadrant 3, both the x and y coordinates are negative, right? Which means both sine and cosine are what? Negative, which means tangent must be positive. So will the what? Cotangent, because cotangent is cosine over sine, that will be positive, right? When we graph, we'll point that out. What about the secant in quadrant 3? Positive or negative? Negative, of course, because cosine's negative. And so will the cosecant, because sine is also negative, right? Okay, so we said all students take, and then what was the last one? Calculus. And that's quadrant 4. So what did the C stand for? Cosine, right? Okay, so what is it really saying? Why is cosine positive in quadrant 4? Because x is positive, right? Isn't x positive? Yeah, of course, so cosine's positive. But that's all it told you. And see, if you memorize this, oh, it's cosine. I don't know what that's telling me, but what they're trying to say to you, look at, if cosine's positive, so is the what? Secant, right? If cosine, in quadrant 4, cosine's positive, sine is negative, so tangent will be negative, so will the what? Cotangent, of course, right? In quadrant 4, sine is negative, cosine is positive, yeah, tangent's negative, and in quadrant 4, cosine is positive, therefore secant is positive. What about the cosecant in quadrant 4? Why is it negative? Because the sine is negative, which means the y-coordinate is negative. So everything jumps back to where? This little picture. Now, let me mention something. If you go online and search like a unit circle Java app, and then they give you a unit circle, and then when you put the mouse on the coordinate on the unit circle and you start turning it, it makes all these triangles change. You'll see everything change. And over here, you'll say, okay, graph the sine function as I move this thing. And as you move it, you'll see the sine function start going like this, right? And you'll see the cosine do this, and you'll see the tangent do what? Any of you seen the movie Saturday Night Fever?
Yeah.
You've seen it? Anybody else seen it? It's back in the 80s when Robert Plant was around. You know, all of John Travolta's dance moves were based on trigonometric functions?
I did not even know that.
It's true. What was his famous dance move? It was the tangent curve. It went like this. I'm totally serious.
I never even thought about it like that.
He did, and then he combined the sine and cosine. What did that thing look like?
So you know the dance.
That was a sine, and then he did the sine function. Remember this one? That was a sine, but then he did a unit circle. You guys think I'm kidding? It's a true story. Go look it up. No, it's not true. I say it's true. Anyway,
Well,
so.
now I'm going to be thinking about, John Travolta actually doing the
You'll never remember. What's a tangent graph look like? You just got to remember where the asymptotes are, right? That was the tangent graph, and the cotangent graph, you took a step over here and went like this. We'll get to those. All right, so I think we're prepped now to start graphing, right? But we're going to take a break. So if you have any questions over the break,
So it will be on your website.
I don't know. Yeah, maybe.
Put it so I can review.
Okay. Anything else, Your Highness? Can I get you a cup of coffee or something? How about a cup of espresso? Okay, no, yeah, okay. Let's take a break here. We'll come back in about 10 minutes, all right? So. All right, let's go. Okay, so now what we're going to do, okay, we've kind of understood where all the trig functions are represented in terms of lengths, right? And this ray and the angle theta and so on, and x and y represent sines and cosines, and how everything relates to all the other 4 trig functions, right? There's 6 trig functions, obviously. So now what we want to do is take a look at what do the graphs look like, and why do the graphs look the way they do? Okay, so you have your unit circle on your table, so I'm going to erase some of this because we need the board space here. So, one of the things to keep in mind when we're doing graphs is to realize the sine and cosine represent the x and y coordinates on the unit circle. Or actually, x represents the cosine, y equals the sine. So, I'm going to probably leave that. I'll probably have to draw a nice clean unit circle up there. Best I can. And as I mentioned earlier, there's a lot of Java applets that will show this very clearly using the computer, so I recommend you go look one up. Probably, Java applet for the unit circle and graphs of trigonometric functions. I wish I had like a nice little tool to draw straight circles, but we'll do the best we can. Okay, x and y. Okay, so the first graph we're going to talk about. Oh, I need to talk about one more thing very briefly here. The differences or the relationship between degrees and radian measure. I mean, what do you remember? Like, how do you convert degrees to radians? What do you remember about that? Pi over 180. Now, what is that telling you? It's a unit fraction. Pi over 180 is a unit fraction. Pi radians is equivalent to 180 degrees. Why is pi radians equivalent to 180 degrees? Where is all that coming from? Yeah, it's coming from the equation of a circle. Now, from the equation of the circumference of a circle. It's really coming from the relationship of the arc length. And you notice on your handout, there's a formula at the very bottom on the left. It says S equals what? R theta, where theta is a radian measure. So very briefly here, when you have an arc, okay, of a given radius, this is S. That's the length of that arc. And this is your theta, we say, in radian measure. And this is the radius. So this is like taking a slice of pizza. It's like a slice of a Chuck E. Cheese pizza, where it's a slice of pizza, right? where there's a radius, there's an angle theta, and there's the length of this arc. How do you relate S, R, and theta? What's the equation that relates those three things? It's right there. S equals R theta. We just said it. S equals R theta. Okay? But see, in the unit circle, if you talk about the unit circle, in the unit circle, and I'll put S with a lowercase u, R is equal to what in the unit circle? 1. So in the unit circle, the length of the arc is equal to what? Theta, correct? That's what it says if R is 1, right? Okay, so what is the equation for the circumference of the circle? C equals what? Well, sorry for asking you such a difficult question. C equals what? 2 pi r. Very good. That's the circumference of the circle, right? Did I say area? Circumference. Okay, now in the unit circle, though, we can say the circumference in the unit circle is equal to what? 2 pi, correct? Because r is equal to what? 1. So see, in a unit circle, the circumference is equal to 2 pi. And what's the length of the arc equal to? Theta. So think about this. If we take the length of the arc starting from the origin and go all the way around the unit circle, what's the length of the arc? 2 pi. Well, the length of the arc is, we say, 2 pi radians. This theta is in radian measure. So let's write that down. We'll say length of the arc is theta radians. And so, like you guys said, you guys are always taught, hey, if you go to 180 degrees, what's the length of the arc on the unit circle? Well, 360 degrees was 2 pi radians, right? That was the length of the arc, which is equal to theta. If you go halfway around, what's the length of the arc? Pi. And how many degrees is that? 180, right? If you go through the first quadrant, what's the length of this arc? Pi over 2, because this was pi, right? Remember? 2 pi, that's pi, this is pi over 2. Where's pi over 4 at? Right in the middle there, right? Okay, so that's why on your unit circle you see these little thick lines here. And those are marking out the pi over 4s, which is equivalent to what? How many degrees? 45, right? Okay. Now, the other lines you have on the unit circle, the little thin ones, these are marking off the 30-degree angles. But in terms of radian measure, 30 degrees has to equal how many radians? Okay, why is it pi over 6? Why is 30 degrees pi over 6? Because it's 1/6 of pi, right? Remember, it's pi over 6 is 1/6 of pi. It's that easy. Pi is equivalent to 180 degrees, right? Because that's the length of the arc. So obviously 1/6 of pi is 30 degrees. What's 1/3 of pi? 60 degrees. Okay. So when you're talking about angles involving pi over 6s, you should be thinking 30 degrees. So what angle in degrees is equivalent to 7 pi over 6? That's where you got to develop your kung fu. Yeah, how'd you figure that out?
Because
It's 180 plus.
Because it's 6 pi over 6 at 180, because that's equal to 1.
That's right.
That's pi, and then it's 1
One more.
That would be 7, which means that's 180 plus 30 degrees.
That's it. It's your kung fu there. It's no memorizing. See, and everybody thinks differently, but we all see it, right? It's 180 plus another 30, right? It's that easy. Okay, so what about 7 pi over 3? How many angles, how many degrees is that? What's your kung fu? 7 pi over 3. Yeah, it's 390. It's 360 plus an additional 30. It would be 390, right? So you start to think that way. Okay. So now we understand the relationship between radians and degrees, right? So when we call out 180 degrees, you can essentially say pi radians, right? We just say pi. So when we start evaluating trig functions, you often say cosine of pi over 6. When they say pi over 6 and there's no units there, you're assuming that pi over 6 is in what measurement? It's in radian measure, right? If someone says cosine, and this, they try to trick you like that in the book too in trig. They'll write, oh, what's the cosine of 2? And they don't put any units. See, just to make note of this before we go, cosine of 2. I didn't say degrees, we said 2. So tell me, is that answer going to be positive or negative? She says positive, he says negative. He didn't say anything. Just kidding. Where is the angle 2 in the unit circle? It's in second quadrant. Why is the angle 2 radians in quadrant 2? Because this is pi, right? 3.14. What's half of pi? 1.57, right? This is 1.57. This is 3.14. So an angle of 2 radians will have to be where? Does that make sense? Because remember, this is pi, right?
Yeah.
Numerically, pi is approximately equal to 3.14. Well, that's the numeric value for it, approximately, right? At pi over 2 up here, that's approximately equal to 1.57. And this is 0, right? Correct. So where's 2 at? 2 would be right somewhere in here, right? In quadrant 2, and therefore the cosine of 2 will be some negative value. To get an actual value, we need a calculator, right? An approximate. We're not worried about that right now. Okay, but now, what we want to look at now is graphs. Now we're going to start with a cosine graph. So before we go on, another thing to remember is the difference between even and odd functions. Okay? Important for calculus too, because when we're integrating even functions over a symmetric interval, depending on whether or not the function is even or odd, is going to can affect the result of your final result. Odd functions are symmetric to what? Even functions are symmetric to the y-axis. What's an even function? When you think of even functions, you should be thinking of x squared. It looks like this, right? Symmetric to the y-axis. What about the odd function? Symmetric to the origin. That one goes like this, right? Okay, right? Even functions, symmetric to the y-axis, x squared. Odd functions, x cubed, right? Goes like that. Symmetric to the origin. Okay. Trig functions, sines and cosines. One of them is going to be even and one of them is going to be odd. Okay. So let's start by graphing one of our functions. Let's start with our cosine. Let's start with the sine. Let's do sine first. Okay. Now remember, sine represents which coordinate on the unit circle? Y. So this is going to be sine of theta, and this is going to be our theta, our horizontal axis. And we're graphing sine. All right. All we have to do is think about, let me finish this thing here. Sorry. All right. So we're starting right here at this point here, at 0. This is 0 radians. We're going to do everything in radians too. Now we're going to graph a sine function, which means when I move this point around this unit circle, we're going to focus on the x or y coordinate if we're graphing sine. We're graphing on y, right? So think of it this way. This finger will be on the y-axis, okay, pointing to the actual value of the y value, which is your sine function. This finger is pointing to the point where the ray intersects the unit circle. When theta is 0, I'm right here on the unit circle, right? And what's my y value? What's my y value here? 0. Now, as theta approaches pi over 2, the point where the ray intersects the unit circle is going to move like this, right? And my y values are going to do what? The y values are now what? Increasing. To what y value? 1. So see, here's theta equals 0. Here's theta equal pi over 6. My y value right here is 1/2. And then I keep going up. My y value right there at pi over 4 is root 2 over 2. When I get up to 60 degrees, my y value is root 3 over 2. And finally, when I get up to the top, my y value is 1. So when theta sweeps from 0 to pi over 2, my y value here goes from 0 to 1. And so how does that look like in terms of the graph? Okay, at pi over 2, I have to be at what value? 1. But what happened in between? What did I say at, if we draw these angles here, at the pi over 6's, that's 1 pi over 6, that's 2 pi over 6, and right in the middle is the pi over 4. Okay. At pi over 6, and this is important for 3B too, second semester calculus. At pi over 6, I've already moved halfway up. I've moved from 0 to where? To 1/2, right? When I go to pi over 6, the y value moves from 0 to 1/2. Okay? And then as you move up, you're going to move closer and closer to, I'll do the best I can here, up here, all the way up here until we get to this point there. Okay? Here's the 1/2, and that's occurring at pi over 6. And in the middle is the pi over 4 one. And I'm just going to do this for the first quadrant. And then over here, I'll put this one weird. Okay. That's that one here. And at the top, we're obviously back at 1. Okay. So see, the first important point, these are the trig functions you have to remember. Pi over 6. What's the sign of pi over 6? According to this graph, the sign of pi over 6 is what? 1/2 on the unit circle. Sign of pi over 6 is right here. You know, if you look at your unit circle that I gave you, what's the coordinates of this ordered pair right there at pi over 6? What's the coordinates there? See, it's root 3 over 2, comma what? 1/2, right? Okay. The y coordinate is 1/2. So this is the nature of a sine function. One thing to remember, when you're graphing a sine function, when you move from 0 to pi over 6, you've already gone halfway up the y-axis, right? That's why the graph jumps up really quickly, right? Pi over 6. And then when you move through, okay, when you're at pi over 4, what's the y value at pi over 4? What's that y value? That's the root 2 over what? That's the root 2 over 2 one. Okay? And then finally, when I get to the next one, this is 1 pi over 6, 2 pi over 6's, which is equivalent to pi over 3. What's the y coordinate at pi over 3? That's root 3 over 2. Okay? So notice, we started at y equals 0, went up to 1/2, then to root 2 over 2, then to root 3 over 2, and then to 1. And those are the values that you're always supposed to what? Memorize, right? Where do those values come from? Why are they so easy to remember? And this comes from geometry. They're from two important triangles. And what triangles am I talking about? The 30, 60, 90, and the 45, 45, 90. So let's draw those triangles separately down here. If I draw a 30, 60, 90 triangle laying like this, okay, this is 30 degrees, this is 60 degrees. It's a right triangle. In terms of the unit circle, we want the hypotenuse of these triangles to be what? 1. See, in high school, a lot of times they teach you these triangles with a radius of what? Of 2, right? They do that because it's easy to remember. In high school, you were taught, okay, the hypotenuse is 2, the shorter leg is half of the hypotenuse, so that one was 1, and this one was root 3. But instead of doing 2, 1, and root 3, we're going to divide everything by 2 to make the hypotenuse equal to 1, so that we can put everything right into the unit circle. So if this is 1 half, and this is root 3 over 2. It's always important to remember the shorter leg is always half the hypotenuse in a 30, 60, 90 triangle. Now, if you look at this triangle and you place it right here in the unit circle, there it is. See, if I drop a perpendicular right here, straight down here, there's my 30, 60, 90 triangle right here. This is 1. This length is 1 half, which is the y-coordinate, and that length is the root 3 over 2. That's why it's there. Now let's go to the next one, the pi over 4. What's the coordinates at pi over 4 off your unit circle? What was it? Root 2 over 2, comma, root 2 over 2, right? This is root 2 over 2 there. Okay. So let's draw the 45, 45, 90 triangle right here. Okay. This is 45 degrees. This is 45 degrees. And we can prove it. We're not going to prove it. We're just going to go back and review again. In high school, you're usually taught that, I think these are 1 and 1 in root 2. That's one way of doing it. That's what we do in high school, I think. But we want the hypotenuse to be what? 1. Now, the rule for 45, 45, 90 is that the legs are 1 divided by root 2, the hypotenuse divided by root 2. But if you have 1 over square root of 2 and you rationalize the denominator, you get root 2 over 2, right? You multiply top and bottom by root 2, and you do get root 2 over 2. I mean, like, one thing to remember, if the angles are the same, then the numeric values of the numerator and denominator have a 2 in it, right? That's one way to remember it if you have to, but by this time you should know that. Okay, so see, if you go back to the unit circle, and if you go to that pi over 4 and drop it down, remember, pi over 4 implies what degree? Pi over 4 radians is 45. That's that triangle there, right? And of course, if the hypotenuse is 1, then both the legs of the triangle are root 2 over 2. That's why those coordinates are root 2 over 2. Right? So it's coming from those triangles there. Now we go here to the pi over 3. And if I drop a perpendicular here, I get this triangle. What kind of triangle is this? This is pi over 3, which is how many degrees? 60 degrees. It's a 30, 60, 90 triangle. It's just that it's this way. And what are the coordinates there? 1 half, comma, root 3 over 2. Okay. And then you're going to see these numbers show up opposite in sign in places, right? But it's always those numbers because they're always coming from these two triangles, right? So a lot of times you're always told, look for the reference triangle, right? Look for the reference triangle and put the triangle in the right place, and then immediately you'll see, hey, this one is a 30, 60, 90 triangle at 5 pi over 6. If this is a 30, 60, 90 triangle, yeah, this length is 1 half. That's the y-coordinate, and it's positive because we're in quadrant 2. The longer leg of the 30, 60, 90 triangle is root 3 over 2, but it's negative because you're in quadrant 2. It's the x-coordinate, right? Okay. You were also told about SOHCAHTOA. What the heck was SOHCAHTOA about? I forgot to mention that when you had similar triangles.
Some old head came hopping through our attic.
Say that again.
That's how I remember it.
How do you remember it?
Some old head came hopping through our attic.
Some old whoop came hopping through our attic. It stands for sine of theta is opposite over hypotenuse. Cosine is adjacent over hypotenuse, and tangent was opposite over adjacent. And if remember those similar triangles, if you look at the x and y's, you'll see that'll tell you, okay, like tangent was sine over cosine. You would see that. Okay, so all right. So notice our graph of sine went from 0 to 1, right? In which quadrant are we in right here? This is quadrant what? 1 of the unit circle. Now we're going to quadrant 2. But in quadrant 2, sign is positive or negative? It's still positive, right? So the graph does what? It comes down and hits here. Where does it hit right here? That's at where? That's at what? At pi, right? Okay. I'll do the best I can. That's my pi. And then it's going to do what? Okay, now this is quadrant what? 2, right? From pi over 2 to pi, it's quadrant 2. That makes sense because in quadrants 1 and 2, all of your y-coordinates are always going to be what? Positive. So if we included our points here, this one was what? Negative 1/2, comma, root 3 over 2, right? And this one here is negative root 2 over 2, comma, root 2 over 2. This is all in a unit circle. And this last one here is the negative root 3 over 2, comma, 1/2. Okay, that's all written nicely on your unit circle. So it's basically following this curve here. And then, now we're going to go to quadrant 3. In quadrant 3 and 4, the y-coordinates are always what? Negative, right? Negative. That means the sine graph will be below the x-axis, right? And so here it is. It's going to come down like this. Okay, here we go to quadrant 3. Where does quadrant 3 end? That's -1. That's, what angle is that? 3 pi over what? 3 pi over 2. And then my sine curve is going to come back up here, and that's going to occur at what? 2 pi. So that's one cycle, because after that, we're going to go around the unit circle what? Again, right? So this would be 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. Next would be what? 5 pi over 2. Next would be 6 pi over 2, which is 3 pi. And so basically that graph, okay, it's not to scale, just to give you the idea, it would come up and then come down again, right? Now what happens, see, a lot of people get confused when you start throwing negative angles. Well, okay, now, this is starting at theta equals 0. If I do all positive angles, then I move this way. But now, let's go backwards. Let's go to the left. If I'm moving to the left on this horizontal axis, how are you moving in the unit circle? Clockwise or counterclockwise? I'm going clockwise now, right? When you go backwards, this is 0, right? So if I'm going to go in the negative direction, remember, theta is always measured from the positive x-axis this way. That's my positive theta. But now I'm going to go negative theta. I'm going to start going backwards. So to go from here down to this angle, what angle is this? If I started here, went to here. That would be negative 90, or negative pi over what? Negative pi over 2. So here, this is now negative pi over 2. And what's happening to the y-coordinates when you move from 0 to negative pi over 2? The y value is going from 0 to where? Negative 1, right? That's why this graph comes down like this. And comes right to here. There it is. Minus pi over 2. What quadrant is this? Minus pi over 2 to 0. What quadrant are you in? You're in the fourth quadrant, right? Because you're right here. You're now measuring negative, okay? And so I go 0, minus pi over 2, and now I'm going back to, now I'm going to where? Negative pi, right? Okay? So look at the y-coordinate. At the angle 0, the y-coordinate is 0. That's this finger here. When I go to minus pi over 2, the y-coordinate went to negative 1. There it is. Now, switch. Now when I go from minus pi over 2 to pi, the y-coordinate is going back to where? 0, correct? How does that translate with the graph? My graph comes back to 0. Minus pi. And what quadrant is this? This is quadrant 4. What quadrant is this? In the unit circle. This is quadrant 4. This is quadrant what? 3. Because you see, this is quadrant 3, quadrant 4, quadrant 1, quadrant 2, quadrant 3, quadrant 4, quadrant, not 5, quadrant 1, right? It starts to repeat, correct? That's what they call periodic functions, because they start repeating, right? Okay, and that's the graph of the sine function. Now, is that graph... Okay, now I got distracted. Okay, we're talking about even and odd functions. So, is a sine function even or is it odd? It's an odd function, right? Now, in terms of calculus, some of you went through first semester calculus. See, if you were integrating a sine function from minus pi over 2 to pi over 2, what would the answer be?
0.
It'd be 0, right? See, those are the things you got to be aware of. If you're integrating from an odd function from negative pi over 2 to pi over 2, this will be a negative area, that'll be a positive area. It would be 0, right?
Is that true with all odd functions?
Yes.
As long as it's at equidistant?
Yeah, equidistance from the origin, right? Yes.
Is parity just a fancy way of saying even or odd?
Is what?
Parity?
Parity. I haven't heard that. I don't know, honestly. I should talk about even and odd functions. I haven't heard that, so I'll have to look that up. Is that what, computer science or something?
I think it's right.
Oh, parity. I don't know. Okay, question?
What's the formula again for that graph? Is it?
The formula?
Yeah, because like there'd be like, can you graph sine equals? I forget it.
Like the,
All the sine values.
Is that just?
this is y equals sine of x, if that's what you're thinking of.
That just
Yeah, if you want to make a table, you know, then you have to realize, and this is important for calculus doing, also trig. When I write this, if y equals sine of x, x is understood to represent the angle, right? And y represents a numeric value between negative 1 and 1, right? Okay, right? Similarly, if you were graphing y equals cosine of x, which we're going to do next, if you're graphing y equals cosine of x, you have to understand x represents an angle, right? X represents an angle, and y represents the numeric value between minus 1 and 1, right? Okay. Now that gets confusing because when students start doing this, and I'll write this out, when we go y equals inverse sine of x, and this gets into calculus. All right, let me fix that to sine here. If I write y equals inverse sine of x, for you calculus students, what does x represent in this equation? And what does y represent?
Y is the angle.
See, yeah, y is the angle, and x is a numeric value between where? Yeah, negative 1 and 1, right?
Well, it's negative.
It's 0 to pi over 2.
Yeah,
because
negative pi over 2 to pi
You
over 2.
can only have
Oh, no, oh, I'm sorry.
function-
No, okay. Inverse sine of x. X represents, okay, what does y represent? The angle. X represents the numeric value, right? What's the restrictions? How can you put x equal 2 into here? You can't put x equal 2 here. Why not? Tell me, why can't you put x equal 2 in there?
Domain's restricted.
This doesn't make sense. Remember, this is the I'm sorry. Yeah, this is the angle here, right? This is the angle, this is the value. We're talking about the sine functions, the y coordinates, right? See, theta can be anything it wants, right? But what are the y values? Y only ranges from where? Okay, on the unit circle. So you got to see, that's why we're getting all tangled up here. Let's do it this way. Sine values. The sine represents the y value on the unit circle, right? And at most, sine can be 1, right? At the least, sine can be negative 1, right? That's it. That's the range, or the range of the sine function, right? This is an inverse function, so you said, what's the domain of this function? The domain of the inverse sine function is negative 1 to 1, right? Okay. And then what was the range? Well, that's a little bit different because look at the sine function. Is the sine function 1 to 1? It's not. Remember that? The horizontal line test, vertical, remember that stuff? That function is not 1 to 1. In calculus, this is inverse functions, right? We're talking about inverse. This function is not 1 to 1. Therefore, we say it doesn't have an inverse function. However, if we restrict its domain, we can make the function 1 to 1, right? So where is it traditionally chosen to restrict the domain? If we restrict this graph from minus pi over 2 up to pi over 2, and only take this segment here, I might as well do this now. and take only this portion of the graph within that green box, is my function 1 to 1 if I just take that? Yes. Okay. So let's talk about that now. Let's talk about the inverse sine function, because a lot of people mess this up. The domain of the sine function as a whole is all real numbers, right? What's its range? Negative 1 to 1, right? But let's restrict its domain. Let's restrict its domain now to pi over 2, negative pi over 2, up to positive pi over 2. Okay, let's restrict its domain. Minus pi over 2 to pi over 2. Is the function 1 to 1 now? Yes. What's its domain then? If I restricted it to where? Negative pi over 2 to where? Pi over 2. What's its range? Negative 1 to 1. Okay, now let's go to this inverse function. Now, since we've restricted its domain, it's 1 to 1, therefore it has an inverse. What's the domain of this inverse function? Negative 1 to 1. That's this value, right? I have to put an x value between negative 1 and 1, and what's its range? Negative pi over 2 to pi over 2. So you have to remember, inverse sine functions, the inverse function of the sine function can only output angles between where? Minus pi over 2 to pi over 2. What quadrant is that? That's 4 to 1, right? It's 4 to 1. Okay, question?
Is that where the symbol comes from in calculus? Like the
No, no.
cursive looking F?
That's
Function? No?
no.
Alright, that's integral of powers and shit.
That's don't worry about that right now. Okay. This is an inverse sine function. So that's one of the, a lot of people mess this up because they don't understand where this thing is coming from. It has a restriction, right? Because you have to restrict sine function to minus pi over 2 to pi over 2. Therefore, its range is restricted from minus pi over 2 to pi over 2, the inverse function, okay? Let's see, we got that, that's fine. Okay, good. All right, so we did a sine graph. We got to do a cosine graph now, right? Okay, any more questions on this? All right. Let's do a cosine graph now. What's a cosine of 0? 1. Why is the cosine of 0 1? I mean, you're walking down the street, and some kid comes up to you and asks you, hey, why is the cosine of 0 equal to 1? That happened to me this morning, by the way.
Measure the x value.
We're going to do this one here as best we can. All right, so let's do this now. I'm going to call this my cosine of theta, and this is my theta. And we're just going to do this really quickly. So basically, if we reference this graph to the unit circle, we're actually making a graph of which coordinate, the x or y coordinate from this one. If we're doing a cosine. X. We're basically tracking the x value, right? Minus pi over 2 and minus pi. Okay. Yeah, we'll throw in a minus 3 pi over 2, just for fun. Okay, let's start at 0. Cosine of 0, I'm right here. I'm tracking the x coordinates now, right? Cosine of 0, the x coordinate is what? 1. And as theta moves from 0 to pi over 2, here's the x coordinate. The x coordinate is moving from where? 1 to where? 0, right? X is 1 here, and as here x is root 3 over 2, here x is root 2 over 2, here x is 1/2, here x is 0, right? So I moved from 1 down to where? 0, right? I moved from 1 to 0 when theta right here moved from 0 to pi over 2. Then when I go from pi over 2 to pi, x is now becoming negative, correct? And moving to what value? Negative 1. So I'm down here at negative 1. That's where I'm at pi. Now let's move from pi to 3 pi over 2. Pi is right here. Okay, here's my angle pi. Okay, and here's my x coordinate right here. X is negative 1. But when I move to 3 pi over 2, notice my x value is moving back to where? The x values are moving back to 0. And then let's bring it home to 2 pi. When I go from 3 pi over 2 to 2 pi, my x coordinate here moves from 0 back to positive 1. How does that look? Okay. From pi over 2, from pi to 3 pi over 2, the x moved from minus 1 back to 0. That's why it comes to here. And then from 3 pi over 2 to 2 pi, I moved from, x moves from 0, right, back to positive 1. And you can see what's going to happen after that. I'm going to start what? Repeating. Okay. Now let's go in reverse. Here's 0. Now we're going to go from 0 to minus pi over 2. What's the x coordinate doing? X is equal to 1 here. Okay, I'm at angle 0. Now I'm going to go negative clockwise. I'm going to minus pi over 2. But notice my x values are moving from 1 to 0. From 1 to 0. Okay. 1 to 0. Yeah, it's a little crooked there. 1. Okay, to 0. Okay, and then when we're at minus pi over 2, we went from 0 minus pi over 2. X went from 1 to 0. Now I'm going to go to minus pi. Notice my x value moves from 0 to negative 1. When I go from minus pi over 2 to minus pi, my x moves from 0 to negative 1. And that puts me down here. And we can keep going if we want, but we're not. And you look at that graph. Is it even or odd? It's even, right? It's an even function. It's symmetric to the y-axis. Okay. Now, for calculus, if you integrated from minus pi over 2 to pi over 2, you could realize that the area between minus pi over 2 to pi over 2, because it's an even function, is twice the area from 0 to pi over 2. Right? That's for calculus.
Would that area be half of a circle?
Too bad.
No. She's trying to strike, are these areas related to the area of the unit circle? There's some relationship in terms of theta, but I'm going to say no. We'll think about that later. Okay, so anyway, there's my cosine function. So let's talk about the inverse cosine function. We know that's an even function. Is it 1-to-1? It's not 1-to-1, right? Fails the horizontal line test. How do I make that function 1-to-1? I want to restrict the domain. Where do we restrict our domain from? If we restrict it from minus pi over 2 to pi over 2, is that function 1-to-1? No. If I go 0 to pi, then my function will be what? 1-to-1. And then we can talk about the inverse. So we come down like this to here. And we go to here to the pi. Here. Okay. Now let's restrict that. Cross this part off to there. And take this off here. And we restrict it to here. Okay, we now restricted our domain. What's my domain now? 0 to pi. What's its range?
-1 to 1.
-1 to 1. Okay. So now, let's look at this graph. Y equals inverse cosine of x. Now remember, y is the angle, right? X is the value between -1 and 1. Okay, so what's this one's domain? -1 to 1. Means you can only plug in x values between -1 and 1. But its range, remember, the range is the angles. The angles that come out of the inverse cosine function have to be restricted from where? Because you restricted that one's domain, therefore you restricted this one's range. So the angles that come out of the inverse cosine are 0 to pi. Which quadrants are those? First and second. It makes sense because to cover all the possible x values, you only need quadrants 1 and 2, right? That covers all the possible x values. Unlike the inverse sine, to cover all the y values on the unit circle, we went from minus pi over 2 to pi over 2. So that's, again, translating back everything to the unit circle. So really the point I'm trying to make is I want you to see everything can be translated back to that, right? Now, we haven't graphed the inverse function. Let's graph this thing. Well, it's not too hard to do. Okay, what's my domain? Negative 1 to what? Negative 1 to 1. What's its range? Oh, I need some more space here, I'm sorry. 0 to pi, right? So let's do it this way. Negative 1 to 1, and we'll say 0 to pi. Okay. Now let's think about this here. What ordered pair is this one right here? What ordered pair is that? That's 0, 1, right? If 0, 1 lies on this function, what ordered pair must lie on the inverse function? 1, 0, right? So where's 1, 0 at? That's right here, correct? All right. What ordered pair is this one right here? This one here. That's pi over 2, comma what? 0. So what ordered pair must lie on the inverse function? 0, pi over 2, right? It's right there. Do you remember one of the a property of inverse functions is that they're symmetric to what? Inverse functions are symmetric to y equals x. So imagine y equals x in here. So it would be, it's not to scale here. So the actual line would look something like this. Okay, not to scale here. But remember, if you take the inverse function and you flip it over, it's going to be symmetric, right? So think about it. If you take this piece and flip it over, it's going to look like this. Like this, right? And so what's happening here is this graph we know is going through here and is coming through here. There it is. That's just taking this piece and reflecting it about the line y equals x. Okay, if you reflect it, then it's going to go like that. If you take, say, this whole piece and flip it over, do you see what it would look like? If I took this piece and flipped it over, do you see it would go like that? Can you see it? Kind of see it there? And so basically my graph does this. It comes up like this. And there it is. This is the ordered pair, negative 1, comma pi. That makes sense because what's this ordered pair right here? What's this ordered pair? No?
0, negative.
Nope. Pi comma what? That's pi comma negative 1. Therefore, that one has to pass through negative 1 comma pi. It's all there, right? And that's the graph of the inverse sine. Okay, so we've got that far. What you should do is, like I said, go to the computer, look up a Java applet for graphing sines, cosines, tangents, and you'll get the unit circle, start playing with that. And just remember that everything is always tied back to the unit circle, and that's what those applets will do for you. So showing you that very visually. So that's about all time we have for today. Hopefully we'll see you again soon. That's it. Get out.